And welcome back, AP Calc students. Time for another FRQ from an old AP exam. This question is from the 2018 exam. It is question number 1. So if you'd like, head to AP Central and you can get a nice crisp copy. Otherwise, you can try to see this one here. Hopefully it's coming through well enough. This is question number 1, therefore it is a calculator question, and the function here they give you to work with is definitely one you have to be careful with entering into your calculator, because the exponents and products, you got to keep track of your parentheses. It's very easy to make an error. Let's see what the question says. This is a style called two rates, so we're going to have a rate in and a rate out, or something's increasing, something's decreasing, and then there was a certain amount there when the time began. And so it's always interesting to see what they decide to do. So on this question, it's people getting on and off an escalator, or getting in line to get on the escalator, we should say. So here's how the problem begins. It says people enter a line for an escalator at a rate modeled by the function r. R is given by r of t is equal to 44 times the quantity, t over 100 cubed times the quantity, 1 minus t over 300 to the 7th. Pretty ugly function here. And that is when the time is between 0 and 300 seconds. And after 300 seconds, anytime it's more than 300 seconds, there's no one getting in line. Maybe the line's too long. So 300 seconds here, if you divide that by 60, you would get 5 minutes. So kind of makes sense. No one's going to get in line if they got to wait for 5 minutes. Or no one's going to keep getting on the escalator. And so r of t is measured in people per second. T is measured in seconds. All right, so there's the rate of increase. People getting on the escalator, there it is. Now let's see what happens for people getting off. It says as people get on the escalator, the exit line at the other end is at a constant rate of 0.7. So there's no vacillation whatsoever, very constant, 0.7 people per second get off. And then there's 20 people in line at time t equals 0. So there's people getting in line to get on the escalator, getting off the escalator. Those are our two rates, and there's 20 people in line when the situation begins. Okay, so fairly straightforward. You could have made this anything, and it just happens to be people getting in line for the escalator. So let's see what they ask for on our very first question here. So here is A. A says, how many people enter the line during the time 0 to 300? Well, as I've stressed several times, whenever you want to get the total amount, or you can ask yourself, what do you get when you integrate a rate? Whatever the rate produces. So this is just begging us to integrate the rate people enter the line, and that's exactly what we're going to do. So the rate people enter the line is represented by the r of t function. So if we just integrate that rate, we should be getting what we're looking for. So how many people enter the line of the escalator during the time interval 0 to 300? Well, what if we just integrate from 0 to 300 the rate people are entering? And the rate people are entering is r of t. And again, what do you get when you integrate a rate? Whatever the rate produces. You integrate the rate people are getting in line for the escalator, you'll get how many people got in line for the escalator. So this being a calculator question, we're going to take advantage of our calculator. That is not a function you want to try to figure out how to integrate by hand. And so we use our calculator. Now, this one is a particularly nasty one to put into your calculator because of all the parentheses and the exponents. You really got to be careful. So I have this already set in here. There's my integral from 0 to 300, and carefully you want to enter that in. And again, keeping track of your parentheses here. I entered all of that, and my variable of integration is x. It's t in the question, but for calculator it's x, and I hit enter, and I get a nice clean 270, which probably might have been anticipating a decimal there. But we get 270, and that would be people. All right, so 270 people got in line in those 5 minutes. It might seem reasonable. Depends how much time you spend on escalators, I guess. Let's move on to part B. Part B says, during the time interval, are there always people in line for the escalator? Or sorry, it's stating, during the time interval, there's always people in line for the escalator. How many people are in line at t equals 300? Now, this is one of those questions where you have to take advantage of the fundamental theorem. And so what I'm going to do here, this is when you integrate a rate, you get whatever the rate produces here. Well, this one is a little bit strange. So let me show you the setup here, what you want to be thinking here. How many people are in line at the 300 or at t equals 300? Well, at t equals 300, how many people are in line? We've talked about creating a function for how many people are in line, or what is a total. And so if you remember back to here, we would say, well, if you ever want the total amount at a given time for one of these two rates questions, and this will be a little bit review, we always have three things going on. We have the first thing is the amount of initial, the second thing is the amount of increase, the third thing is the amount of decrease. So what I want to do is build this function, and then we'll look at it. And you almost always have to do this in a two-rate question. So let's see. First off, I'm going to say what is the initial amount, and then we are going to add to this the integral from 0 to t, usually, the amount of increase, and then we're going to subtract the integral from 0 to t of an amount of decrease. So we'll see, this is just sort of a template. This isn't really precise yet, so let's see what we can start filling in. So a of t is equal to, let's see if there was a hint in the problem for an initial amount. So as we read through here, and it's usually right at the end, and sure enough, there it is. There are 20 people in line at t equals 0. So my initial amount is the 20 people in line. Got it. Now I'm going to integrate from 0 to 300, because they actually want us, they're asking how many people are in line at time t equals 300. So if we integrate from 0 to 300, the rate that people got in the line, and we actually already know this number from the prior problem, so that's how many people get in the line, that's how many people were in the line, and now let's subtract how many people got off. So we would integrate again from 0 to 300, and what does it say about the rate of decrease? It says, in the original question, it says, as people get on the escalator, they exit the line at a constant rate of 0.7 people per second. So the rate there is just a constant 0.7, and that'll be dt. So that's actually the setup for the amount. I want to make one little adjustment here. At any given time here, I was working ahead here. Actually, this should be t. I was one step ahead. I was combining steps. We've talked about how if this is unknown, these variables have to be different. You can't have the same variable in your interval as your integral. And so I was already partway on to my next step here. So let me just make that little adjustment. Okay. Now the question is saying, what is it at 300? How many people are in line at the 300 second? Now I would say 20 plus the integral from 0 to 300 of r of t dt minus the integral of 0 to 300 of 0.7 dt. Now I can do that. Now for some of you, you might want to combine this into one integral, and that's fine. But here's your setup, and this is a common theme, even with position, velocity, acceleration questions. You have your amount is always three things. Initial plus the increase minus the decrease, there it is. Set up your generic form of your integral, and then go and put in the t-value they're asking for. So they're saying 300, there it is. Well, for this particular question, they actually gave us quite a bit of info. They said, well, 20 is there. We did this, 0 to 300, we're going to borrow that from here. That was 270. And then we have to subtract this integral. Now, for some of you, you can probably do this in your head. You can see that the result of this integral is going to be 0.7t evaluated from 300 to 0. If you didn't notice that, you can just put that in your calculator. But in either case, you're going to get 0.7 times 300. And 0.7 times 300, you're going to get a nice clean number. And we'll just put that over here. Actually, we'll go ahead and just throw the whole thing in there. So let's pretend you didn't quite notice this. That was going to be a very easy integral. So you just said 0 to 300, and your function is 0.7. Whoops, and there's x. And you get 210, and 210 is 0.7 times 300. That's what was going to wind up happening. So pretty nice number here. We get 290 minus 210, and we get a total of 80. And so during the time interval, how many people are in line at t equals 100? T equals 300, there are 80 people in line. So there are 80 people in line at t is equal to 300, or at the 500-minute line. Okay? And again, the amount equation, that is a very common thing. You always have to do that with two rates. Okay? Now, time for part C. All right, and let's get this out of the way. And let's see what we can put up here. So part C says, when the time is greater than 300, what is the first time that there are no people in line for the escalator? Well, what's kind of strange here is once you get over 300, there is no more increase. You're just going to have to deal with, there's no more increasing, it's however many people were in line. So like a typical AP question, you're always building on earlier information, and we're going to go right back to B and see, well, what's going on at 300? Well, at time equals 300, there was 80 people in line. So since nobody is adding, how long does it take for these 80 people to get out of the line? So if you did this correctly, we're going to need that 80. So let's go and just put this up and let's think through this here. There's 80 people in line. Nobody is joining, but these 80 people in line, according to the problem, are exiting at a rate of 0.7 people per second. So how long does it take 80 people to get out of line if they're leaving at 0.7 per second? Well, this is one of those things, just the wording of it could be a little bit confusing, so I'm going to give you an example. If you are given a rate, and you're given the total from the rate, you just have to figure out the time. I'm going to give you a simple example from distance equals rate times time. Here's an Algebra 1 question. So this is just a little note, just so you don't get lost on the explanation here. Okay, so what if I told you this? What if we know that distance is equal to rate times time? So what if I told you that you were going 60 miles per hour? And what if I told you your distance you traveled was equal to 120 miles, and I asked you, what was your time? Or how long would it take you to do that? I gave you your rate, it's right there. I gave you your total distance traveled, which is right there, and I just want you to solve for time. So you would just say, well, I went 100, you do this in your head, I went 120 miles, I was going 60 miles per hour, and I'm going to solve for time. Divide both sides by 60, I get 2 is equal to my time, or 2 hours. Well, in the similar fashion, that's what you guys are given here. You're given how many people are in line, and you're given how fast they're getting out of line. We just wanted to see how long this is going to take. So what we have here is we need how many people need to exit the line is equal to the rate they're exiting the line times the time. This is the equation. Instead of D equals RT, it's exiting is equal to rate times time. So the rate they're getting out of line is 0.7. We're solving for the time, and the amount left in line that need to exit is 80. So you just divide both sides. So 80 divided by 0.7 is going to equal 114.285. And this was one of those weird questions that this was a pretty high miss because it was just weird the way it was presented. And this actually is not the right answer. This is the most common wrong answer is right here. So it looks like it took this much time. But the original question says, for time greater than 300, what's the first time there's no people in line? Well, it's this on top of the original 300 seconds that got us to 80. So I think you could probably tell just the wording of this one. Part C was a low percentage get for a lot of people. So it was this amount plus the original 300 seconds. So the final answer was 414.285 seconds. So this little part right here, this example, this was just a little illustration to show you how I was getting this. So I could have just said, oh, divide 80 by 0.7. But what you're doing is you're dividing your total amount by the rate to get the time, just like you would with travel. So hopefully that made sense. So there is our answer right there. Now it's time for part D. For the time between 0 and 300, at what time is the number of people in line a minimum? Minimum. When you guys hear minimum, you should be thinking critical numbers. You should be thinking derivative. And it says to the nearest whole number, find the number of people in line at this time, justify your answer. All right, well, this goes back to why it was important on B to figure out the amount of people in the line, which was right here. And that's the equation we are going to take the derivative of with respect to time, and that'll give us, then we'll set that equal to 0 and undefined. So we've done this several times. I'm going to do it again here. I'm going to take the derivative of the amount of people in the line. We'll take the derivative of it, and then we'll set it equal to 0 and undefined. So I'm going to rewrite this right here, recopy, and say, all right, I have a of t, and that is equal to the initial amount plus the integral of the rate people are getting in line, and I'm going to subtract the rate people are getting out of line. And that equation I need to take the derivative of. So remember, when you're taking the derivative of an integral, so technically here's what I'm doing. I'm taking d dt of this whole thing. So a prime of t is equal to, the derivative of that is 0. And here's that tricky part again, where I'm going to, the derivative is canceling out the integral, but I have to replace the variable with the variable of the interval times its derivative. So remember, here's that 4 spots that takes place. So I'm going to have r of t times the derivative of t, which is 1, minus r of 0 times the derivative of 0, which is 0, minus this one is the, again, the derivative cancels out the integral, so it's the function value at t, but it's a constant, so it's just 0.7 times the derivative of t, which is 1, minus 0.7 again times the derivative of 0, which is 0. So if you recall, I've tried to stress this a lot with the second fundamental theorem. When you're taking the derivative of an integral, you have 4 little pieces. But almost every single time you do this, almost all of it drops out except for one little part. So what wound up being the derivative of this thing? 0's gone. All this drops out, and we just wind up getting r of t minus 0.7. That is the derivative of the function. And we have to take that, and we have to set it equal to being undefined. And when is that thing equal to 0? Okay, well, it's never undefined. We're never going to get values from there. And again, you guys, r of t is this really wacky equation here of 44 times t over 100 cubed times 1 minus t over 300 to the 7th. Just nasty. So this is, again, being a calculator question. What you're going to do is, when does this equal 0? Well, in your calculator, what I would do is I would put in r of t, this crazy function, and I would set that equal to 0.7, and then see where they intersect, and use the intersect function on your calculator. When you do that in the interval, remember this has to be, they're explicitly telling you between 0 and 300, what you're going to wind up getting are these 2 intersections. Calculator, you're going to take the function r of t and set this equal to 0.7, and then find your points of intersection. And for the sake of time, and clarity here, you can do that in your calculator. Y equals, and put in this, the crazy r of t function they give you. Then also graph y equals 0.7 and see where they intersect in this interval 0 to 300. So you're going to have to manipulate your window a little bit. And when you do that, you're going to get 2 times where they intersect. And here's what you're going to get. You're going to get t is equal to 33.013. Rounded. And the second time it happens is at second 166.575. And just for the sake of time, I'd already put these 2 functions in the calculator, but you can see I want to see where they intersect. And so r of t is this top function here. So there's the 44x over 100 cubed times 1 minus x over 300 to the 7th. And the second function is just y equals 0.7. And so on the graph, the question is, when do they intersect? Now I had adjusted my window to be from 0 to 300. So I think you can see there's 2 points of intersection here. There's the first one, and then here's the second one. And you can go through your steps with how to find intersection points. And what you're going to get are these 2 values here. There's the 33 as the first one, and the second one, a little over halfway, you can tell, is about 166. And you have to adjust your calculator for the window. So I immediately changed my window to 0 to 300, and it was still manageable. Then I went in and changed my y-axis a little bit, so it's a little bit easier to see. So that would be the process of doing that technology-wise. And then we come back to here, and so there's my values. So if you'd like, you could say, well, I have 2 critical numbers here. And so I have my endpoints that I have to check. And so what some people like to do is they say, well, I want to get a feel for what's going on. So I'm going from 0 to 300. And my 2 other times here are 33. I'm just going to put 33 and truncate that, and 166. And I want to know whether it's increasing or decreasing. If you'd like to do this, this is a fine approach, but it's a little time consuming. You might not have the time to do it because the question just wants to know when is the minimum. When's the minimum amount of people in line? So knowing increasing and decreasing might allow you to eliminate some values, but it tends to not really help you too much with the time. So the best thing you can do is to just test each point and see what they're going to give you. So I'm going to go back to my amount of people in line and see when it was the smallest. So what I'm going to do, I'm going to draw a line here just to give myself some room, and I'm going to go on the bottom here. I'm going to say, well, if these are my values that I have to check, and then also the beginning and the end, I'm going to come over here and see what's going on, how many people are in line when the day begins. Now, I could put this into this equation right here to get it, but no need to. It's pretty straightforward, pretty clear in the question. There was 20 people in line. If you'd like to do this, you're still going to get 20. So there's the first one. We have 20. Got it. Now we're going to compare it to the next one. What happens after 33.013 seconds? Well, I'm going to find my amount at 33.013. Well, what's nice is in your calculator, if you have saved the work from before, you can just go in and edit, and it's not bad at all. So earlier in the problem, we had found, we had done our work here. We have a lot of this already in here, and we could say, well, I'm just going to go up here and edit this, and we'll add the 20 and we'll subtract the other part here. So I'm actually going to enter there and go back to here and just change my 0 to 300, and I'm just going to change that to 33.013. I have that there, and then I'm going to subtract. I will get that value right there, and in the same integral, I'm just going to say, or in the same line of data here, I know that I'm going to wind up subtracting the integral from 0 again to 33.013, and the function there is just 0.7, and there is x, my variable of integration. So if I do all of those, let the calculator do the work, I get negative 16, but I have to remember my initial condition, which was 20. So I add that on there, and I get 3.803. So far, that's the smallest. So I have 20 at 3.803. And now let's go to the next one, which is 166. And 166.575. And again, in your calculator, this is great, because all we'll have to do is just go back and edit. And so go back up to here to this step, and I'm going to hit enter. And now I have this being, I can just edit this, and I'm going to go in here, and we have 166.575. And I know some of you would have written this in one integral, and that would make it even faster right here. But I'm going to, I have it set up this way, so I'm going to keep going. So 166.575. Okay. And so that's obviously a little quicker there. And let the calculator do the work here, and don't forget to add 20 at the end. 138, and then we will add our plus 20 from our initial condition. It looks like we're getting 158.070. 158.070. Okay, so we have that one, and then we have A of 300. But A of 300 we had already found from before, and that was 80. So try to keep my work straight here. I'm going to say A of 300 was equal to 80. So there's the four values that I needed to check all right there. And it clearly looks like the 33 seconds would be this. And they want this to the nearest person, so 3.8 would be about 4 person. So the fewest number of people in line, or the number of people in line, is a minimum at t equals 33.013. I'll move this out of the way a little bit. And we'll write that a little smaller right there. We knew A of 300 was equal to 80 from before. So the number of people in line is a minimum at t equals 33.013 seconds with 4 people. And there it would be. So, from the top, a 2 rates question. It's rate people are getting in and out of line for an escalator. So, question number 1, how many people got in line in 300 seconds? Integrate a rate, get what you get, 270, no problem. Second one, that was the function build. Build the equation for the amount of people in line at any given time. A of t, initial condition, plus the rate of increase, minus the rate of decrease. And then they wanted it at the 300 second. We just substituted in, and we got our value here. Letting our calculator do the work. Question C was the kind of the weird one. When are there no people in line? The way you could do that, you could say, well, after 300 seconds here, we were just worried about people exiting, and it was a little bit weird. It didn't follow. You kind of had to logically just think through it. I have a rate. I have the amount left here. I had to figure out the time, so I just divided. This is really intuitive for some, but really hard to see for others. Not a huge deal. And D was the big money question. There was a lot of the points there. And it's at what time is the line a minimum? You hear minimum, you think critical numbers. You think derivative. You think derivative of your amount equation. And then you remember second fundamental theorem. How do I take the derivative of this? Remember your 4 points for each derivative of the integral. We get it down to here. This also, there are some of you that are really, you can see the big picture a little bit better. Some of you can develop that equation on your own without even actually doing that step. We get our critical numbers, we test them, and we find out it's 33 seconds, is it? Okay, so there it is, AP Calc AB 2 rates, 2018, number 1. Thanks for watching. See you next time.